Hello, I'm Wayne Strasser, and I'll be moderating the panel today titled Industrial Multiphase CFD Risk, Rewards, and Remorse. Our panel lineup is as follows. I'll give a brief introduction, followed by Dr. Broshany, Dr. Farrell, Dr. G, and Dr. Morales, and then we'll all have a group discussion lasting approximately 20 minutes. I'll give a very brief introduction of my work history. I spent 25 years in the chemical and transportation industries before moving into academia. During that time, I was focused heavily on multiphase CFD, and I found more often than not there were opportunities for failures more so than successes. The purpose of this panel is to expose the risks of CFD and to warn newcomers and those who by default trust computer programs that things aren't always the way they seem. So to dive a little more deeply into the purpose of our panel, I'll give you the official abstract here. As computer processors and memory improve, CFDs become a valuable tool for analyzing fluid flow and heat transfer. However, as with any numerical tool, the use of CFD is interlaced with the good, the bad, and the ugly. With the proliferation of highly commercialized CFD tools, there's a tendency to produce results without understanding and avoiding pitfalls. Here, we explore some recent successes and failures in this arena. In order to help set the stage for this panel, I'll remind the audience of what CFD stands for via a few definitions I've provided. These are not my originals, but I am repeating some of those I've heard throughout the years. The first is continuous frustrations and divergence, colors for directors, catastrophic failures and disappointments, compelling fluent disillusionment, and lastly, confusion, flailing, and denial. In the lower left-hand corner, there's an illustration describing what happens when we divide by zero, which is often available in multiphase flow problems. In the bottom right-hand corner is a picture of the components of a CFD problem. We begin in the green section of the pie chart, describing how we would cheat on the geometry to make it amenable to meshing. And then we have our algebraic manipulations solving the problems, and then following up with substantial amounts of prayer to make a useful problem. I attempt to illustrate with this progressive table the cumulative effects of those factors which lead to our discomfort with multiphase CFD. The first of those is continuum mechanics. We have a very low fear factor with continuum mechanics because we trust that the Navier-Stokes equations accurately represent transport processes for continuum mechanics. The second is RANS modeling. We know that RANS is far from perfect, but we have a low fear factor. We typically understand the limits of our RANS modeling, where they can and cannot be applied. Then comes the assumption of interpenetrating continua. Thinking about the two-fluid model with multiphase flow, for example, we have a low fear factor with this. Again, we understand the limits and use this successfully for years. Then we get to multiphase RANS. Clearly, the concept of Reynolds-Navier-Stokes with bubbles, droplets, and the shapes in between gives us a reason to be concerned about the applicability of RANS in those situations. Then you think about multiphase exchange terms in turbulent media, and we get a little bit more fear, we get a significant amount of fear related to the fact that those exchange terms are often calibrated at conditions outside of typical industrial processes. So we're limited in our ability to apply those to our real flow situations. Then lastly, the combination of all these, you consider the cumulative effect of all of this uncertainty. We have to say yikes and be very concerned with what we're assuming and how we're applying the different routines that we're using to solve these problems. I'd like to share a few of my favorite gotchas, those things that have caused trouble for me over the years of using CFD for multiphase flows in industrial situations. I think we're fairly comfortable with the concept that CFD doesn't always match experiments. However, sometimes in multiphase CFD, results don't even match experimental trends. Secondly, sometimes results don't even match well-known physics. Thirdly, it's important to note that sometimes a change in an assumption, a computational degree of freedom, such as turbulence model, can lead to directionally different results in a comparative study among various permutations. We tend to think that, such as with a RANS model, that even though the model's wrong, we can at least assess the directional changes we expect from different design permutations. However, as I said, I found that doesn't always hold true. Next, I'd like to talk about briefly what ANSYS is kind enough to share with us, and they call them Class 3 errors. Those are those that are invisible to the user. They continue to allow us to make colorful pictures that could be completely erroneous. One of those was from CFX version 13. In that case, the code did not know which direction in the LES scheme was upwind. I consider that a major issue, and the user would have had no idea had CFX not been kind enough to share that with us. Next is a much more recent example with Fluent version 19. The user can specify a time step. It turns out that the main flow equations would follow that time step routine, but scalars and species and other things would not necessarily match that time step setting. They would use the default setting of 1 second per time step. And very importantly, sometimes local point monitors continue to dance and trend, move around long after the residuals flatten. But the code assumes that we can just trust residuals and have residuals being checked for convergence, all being on by default. So in short, we're going to show today that CFD should be handled with care.